Part 3 of Unit 2 is Net Ionic Reactions. A net ionic reaction only shows the parts of a reaction that are actually doing something. We often see reactions that take place between aqueous solutions where most things stay dissolved. Those things that stay dissolved in water, they're not going to actually do anything in a reaction. Yes, they're there, but they're not combining with anything. They're not making any new compounds. So we're going to get rid of them in a net ionic reaction. Those ions that don't participate in the reaction, that are left out, those are called spectator ions. So I found a good picture of like 65,000 spectators here. OSU fans, I hope you appreciate this. This was that night when we finally were able to be the ones to say scoreboard for a year, when we curb stomped the Dirt Burglars 44-10. Until next year. Anyway, we identify spectator ions by looking at things that are in aqueous solution before and after the reaction. To figure that out, you're going to have the solubility rules memorized. If something is an ion on the reactant side and it forms a solid precipitate on the product side, that means it's actually done something in the reaction. It combined with something else to produce that solid. If it's an ion on the reactant side and stays dissolved as an ion on the product side, it's a spectator and we can get rid of it. So the only things we're going to be crossing out are ions. We're going to be leaving in solids, liquids, and gases. Elements that are in their natural state, they're either going to be solid, liquid, or gas. Nothing exists as an ion naturally, so we're not going to be getting rid of them. We have to know the solubility rules to determine if an ion will turn into a solid precipitate. Insoluble products are either solid precipitates or they're going to be weak acids or bases that don't dissociate. Soluble products are ions that exist in aqueous solution. So this part about weak acids and bases not dissociating, strong acids and bases turn into ions 100% of the time. Every single HCl will break up into a H plus and a Cl minus, because hydrochloric acid is a strong acid. So HCl is always going to be H plus and a Cl minus. Likewise, sodium hydroxide is a strong base. NaOH, 100% of the time, is going to dissociate into an Na plus and an OH minus. We've only got a limited number of strong acids and bases that, yes, you will have to memorize. An example of a weak base would be something like copper hydroxide. That's not going to dissociate into ions. You're going to leave it written together. An example of a weak acid would be something like nitrous acid, HNO2. Those don't all dissociate. A lot of them stay together as one molecule, so we're not going to be breaking them up. There's some general trends in solubility. Most of the time, salts, or ionic compounds of these elements, are going to be spectators if they're in aqueous solution. Potassium is quite often a spectator. Nitrate, sodium, ammonium, and acetate, those are all very soluble ions. They dissolve most of the time. Sulfate is quite often soluble. It's only insoluble when it's with heavy metals like barium or lead. Only strong acids dissociate into ions. Weak acids don't. I know I kind of just described this on the other page, but here's that list of strong acids you need to know. HNO3 is always going to dissociate, but HNO2 won't. That's a weak acid. The other strong acids are HCl, HI, HBr, HClO3, that's a polyatomic ion, HClO4, and H2SO4. Yeah, those 7 acids will 100% of the time dissociate into a hydrogen ion and whatever the anion is. All other acids are weak acids. They're not going to dissociate. You're going to leave things like HNO2 together. Same concept applies to strong bases. Only the strong ones are going to dissociate. And the strong bases are the alkali metals. That's the ones in group 1 of the periodic table. And strontium, calcium, and barium. They're the alkali earth metals, second group on the periodic table. If you look at the periodic table, these metals make kind of a lowercase b on the periodic table, so that's one way to remember the strong bases. So strontium hydroxide, calcium hydroxide, barium hydroxide, they're going to dissociate 100% of the time, but others, like copper or iron hydroxide, are going to be weak bases that don't dissociate. Net ionics matter because question number 4 of the AP test is always 3 net ionic reactions. Questions are given in this form: solutions of barium nitrate and sodium sulfate are mixed. That's an easy example, but that's all the wording you get. You're expected to be able to write both the reactants, the products, balance it, and cancel out any spectator ions. And there's also a follow-up question that goes with it. It might be identify what the precipitate was in this reaction. There are 3 questions, and each one's worth 5 points. So if you are good at net ionics, this is a money question on the AP test. So we're going to do several examples here. Solutions of lead nitrate and potassium iodide are mixed. Right here they told us that these things are solutions. That means they're dissolved in water. So normally we would write this as lead 2 nitrate and potassium iodide. They're mixed. It's a double replacement reaction. We're going to get KNO3 and PbI2. We need to go back and balance it real quick. We'll throw a 2 right here to balance the nitrates, and that means we also have to put 1 over there. So now our equation is balanced. This is our balanced equation. We need to take this and blow it up. We're going to write a complete ionic equation. In a complete ionic equation, everything that's soluble is broken up into the ions that go into it. So since both of the reactants are aqueous solutions, we're going to split them up. We're going to have a lead ion. We're going to have 2 nitrate ions because of that subscript. We're going to have 2 potassium ions and 2 iodide ions. Now looking at the product side, if you know your solubility rules and listen to what I said earlier, you know that nitrates are generally soluble, and that's the same way with potassium. So we're still going to have 2 potassium ions and 2 nitrate ions. Lead forms precipitates a lot because it's a heavy metal. So lead iodide is our solid precipitate. It's actually yellow in this reaction. So since it's a solid, we're going to leave it written the way it is, PbI2. In this complete ionic step, we go through and we cross out things that are ions on both sides of the reaction. So we've got 2 potassium ions here. We can cancel those out. And we've got 2 nitrates that can be taken out of the equation. So our net ionic equation, which only involves those that are actually participating in the reaction, is everything that's left. We've got lead plus 2 iodide ions is going to yield PbI2. That's it. That's your answer for the net ionic reaction right there. So we have to identify the spectator ions and get rid of them. Let's look at some more examples. Copper wire is placed in a solution of silver nitrate. Well, they told us this is copper wire. It's just metal by itself. And we've got a solution of silver nitrate. So AgNO3. This is a single replacement reaction. Copper is going to switch places with silver. So we're going to get some silver metal precipitate, and the copper is going to dissolve. That's our complete balanced equation. Now we need to write the complete ionic equation. Nothing special happens to copper because it's just a pure substance by itself. But this is a solution, so it's going to break up into an Ag plus and a NO3 minus. Now on this side, we've got our silver metal, and our copper nitrate is going to be a solution because nitrates are always soluble. So we've got a copper ion and a nitrate ion. So now we need to identify the spectators. Copper is just a solid on the reactant side. That's an ion on the product side, but they're not the same, so we don't cross them out. Silver is an ion on the reactant side and solid on the product side. They're not the same, we don't cross them out. Nitrate is the only thing that exists as an ion on both sides, so we're going to get rid of nitrate, and whatever's left is our net ionic reaction. So we'll have copper plus silver ion yields silver plus copper ion. Let's look at the second example. Propane undergoes incomplete combustion. C3H8 plus O2, and that's going to yield, since it's incomplete combustion, carbon monoxide and water. Now we still have to have balanced equations in net ionics, but if you notice, we've got either a liquid or a gas and 3 gases. There's not going to be any spectator ions with a combustion reaction, so all we have to do is make sure we've written the balanced reaction correctly. So we've got a 3 for the carbon on propane, so we'll put a 3 right here. We got we got an 8 on hydrogen, so we'll put a 4 here to make 8 hydrogens on the product side. Now for us to balance oxygen, we've got 1, 2, 3 oxygens from carbon monoxide and 4 oxygens from the water. That adds up to 7. We can't put a whole number here that multiplied by 2 will equal 7. We'd have to put 3.5. We need to have whole numbers as our coefficients. So what we have to do is multiply the entire reaction by a coefficient of 2. So we're going to insert a 2 in front of the C3H8. We're going to have to double these. This becomes a 6. This will become an 8. So that means we've got 6 plus 8. We've got 14 oxygens on the product side. Now we can put a 7 there and have our whole number. 7 times 2 is 14. So that reaction with the red coefficients would be your net ionic reaction. There are no spectators for you to cancel out. And one last example. Remember, strong acids and bases are going to be broken up into ions. Weak acids and bases are not. Nitric acid is a strong acid, and sodium hydroxide is a strong base. So our complete balanced equation would be HNO3, our nitric acid, plus sodium hydroxide. That's going to yield HOH, or H2O, plus sodium nitrate. Our complete ionic, since these are both strong, a strong acid and a strong base, they get split up. We have an H plus an NO3 minus plus an Na plus a hydroxide. Water is a pure substance. It's a liquid, so we're going to leave it together as HOH. Sodium nitrate, that is a soluble salt. Nitrates are always soluble. So we have Na plus NO3 minus. Now we need to go back and cross out any spectator ions. Hydrogen, not an ion on both sides. Nitrate is an ion on both sides. So is sodium. So our net ionic for a strong acid and strong base reaction, H plus OH minus, is going to yield water. Neat little fact about strong acid, strong base reactions. Your question for this section: aqueous sodium chloride is poured into a silver nitrate solution. Again, do your best to type the whole balanced net ionic equation into the answer box.